So first off, I want to thank you all for coming today. I plan on making these sessions, so every period from this point on, I plan on having an optional session like this for the duration of the network outage on campus. There is no word as to how long the network outage will be. As far as I know, the only date that we have is November 30th, and that's for the restart of registration. So the reason why I'm having difficulty providing this session, if we were in person, we would definitely still be working through that. We'd still be having regular class schedule. But the issue is that there are a number of your colleagues who have, and maybe some of you do as well, if you have access to the internet. But since there's no access to internet on campus, doing remote from campus is impossible. And I don't expect folks to run between Starbucks and campus for this class. So that is why I've moved everything asynchronous. But I will be providing at least once a week an optional session to go over the week's material. Of course, once if the network issue has been resolved, we will go back to our regularly scheduled programming. We are on our way towards the end of the semester. We are dealing with a few more complex statistical tests, and because of that, other than today, the ANOVA stuff will be as far as I remember, and I'll double check when we get into correlation or regression, but this will be the last time that you're going to have to actually know how to do the statistical test from scratch. So actually doing the equations. The ANOVA equations aren't particularly difficult. They look a little bit difficult, but they're not really difficult once you sort of start putting them in R. But this will be the last time you have to do that. The remainder of the statistical tests that we do, our non-parametrics and our correlation regression, will all use the built-in R function. So this is the last one that you'll actually have to do sort of the by hand or the long form of it. I would like to have these sessions every twice a week because of the fact that this stuff is a little bit more complicated, but it's just, I will make sure that when we do have asynchronous days, that you'll have all the material that you need to be successful and to do your portfolios and to be successful in the quizzes. Another announcement I'm going to make, this is recorded, so I'm going to make this announcement, but I'm also going to make it over email. I decided to do this before the network outage, but I forgot to announce it. I will be dropping your lowest quiz grade. So once all the quizzes come through, I will go through and I will actually drop the lowest one. I don't know how these quizzes are going to go for the next few weeks. I'm going to increase the time. Not this last one. So the one that's this week is still 15 minutes. But the ANOVA one and then any of the next ones will be at least 30 minutes each. And I do plan on dropping the lowest quiz grades. I also will reevaluate the grading scheme if this network outage continues for past the Thanksgiving break. Okay, so what I'd like to do today is just go over ANOVA. Let's just practice it. Let's open up R and let's just do an ANOVA, because ANOVAs really aren't that much more complicated than a 2-sample t-test. It just increase our samples. So if you go to the Brightspace page, you should have, let's see here. Oh, That looks weird. Is that all coming in like green and purple for all of you?
Yeah.
Yeah.
Yeah. Okay, that's interesting. Let's see here. I think
It's kind of cool, actually.
you know what? Are those coming in normally for you though?
Yes. It's just
Okay.
your camera that's weird.
All right, it looks like that fixed it. Okay. Sorry, the setup I was not prepared well with this setup. Let's see here. Okay. All right, it looks like I fixed it. So there's this. All right, so first off, if you go to the Brightspace page, I just put up the ANOVA R script from this video. I should have posted that initially, but I've forgotten to. So if you click on that link, it will, you can't see it, but it will pop up a download window, and you can just download the R file. So if you want to take a moment and download that file, it'll make your life so much easier than trying to write it all by hand.
Where's the download? I'm so sorry.
So if you go to content, you go to where the videos were for chapter 15, the analysis of variance stuff. So that's the first video with the three squirrels. There's a link right on top of it. So click here to download a script from this video. You click on that and you should be able to.
Yes, thank you so much.
And if you, once you have it, just throw up a thumbs up or some sort of emoticon.
Professor, for me, I'm having trouble with Brightspace. Can you hear me?
Yes, I can hear you. Let me see.
Wait, I'm gonna.
Here, I'll put it in the chat. So here's a link to the box. See if that works. I put it in the chat. If you're having issues with Brightspace and you can't get to the videos, you can go to search. Actually, I'll just give you the link. I'll send that out as a message as well. If you're having trouble with the Brightspace issues, are not the campus considers that we don't have an issue with Brightspace, and it's starting to seem like we do. So if you search Lundquist Urban Ecology Lab on YouTube, everything is, and you go to that, and I'll just put the link to the channel here. You can actually find all the videos up on YouTube, and you go to playlists, and you can go to biostats, statistics, and I have a playlist of every single video. So we are on to one-way ANOVA. You'll only be able to see one of these. One of these is hidden. And then the stuff for next week. So if you need those videos and you can't get them on Brightspace, you can still find them on YouTube.
Thank you so much, Professor. I was able to download the ANOVA R.
Great. Okay. So there's that. Okay. Everything's still coming in? You can still see everything? I'm running on a single screen here that's ultra wide, and so I'm trying to, like, you're over here on this half, and then this one I'm not at all for home-based stuff. I was so excited to be able to do everything from the lab. Okay, so that's the video. So you have the R script downloaded. Why don't you open it up? But let's talk a little bit about what ANOVA is before we delve into the R stuff. But you can open it up and be prepared for it. Okay, so what is ANOVA? So ANOVA stands for Analysis of Variance, and so we just shorten it to ANOVA. And basically, what ANOVA is just a t-test that can compare more than two means to each other. So if you are interested or compare more than two groups together. So let's say we have the iris data. So the iris data has three species: Iris setosa, Iris versicolor, and Iris virginica. We could technically, let's say we're interested in the differences in the sepal lengths, whether there were species differences in sepal lengths. We could compare each species to each other. So we can do a two-sample t-test to compare virginica to setosa. We could compare versicolor to setosa, and we could compare versicolor to virginica. So that's three different comparisons, since we have three different species. The problem with that is that it's clunky. And it also, there is an issue when you do multiple statistical tests on the same data set. Anyone have any idea what that might be? What that issue might be if you just constantly taking different bits of your data set and comparing different parts of it to each other?
It won't be random?
Well, it's not. No, I mean, it's not. The data was collected. You know, we assume that the data was collected from a random sample of each species. But what happens if you constantly retest your data? What are the two things that can happen when doing any statistical test?
Type 1 and type 2 errors?
Type 1 and type 2 errors. So the type 1 error is a false positive, right? And a type 2 error is a false negative. What was the error rate for, or what is the rate of type 1 errors for when you're running a statistical test? Anna, do you know? Do you remember what percentage of time would you expect to commit a type 1 error?
I don't remember the exact percentage, but isn't it like more likely than type 2?
Not necessarily. And you should know the exact percentage. You should all know the exact percentage. It's built into all of our statistical tests.
Is it 5%?
It's 5%. So it's a 0.05. So that alpha, right? So it's the alpha, the 0.05. That is our false positive rate for any statistical test. And so how many tests? Does anyone know how many times you would have to run a particular statistical test to get the to commit a type 1 error? Out of how many tests do you perform, how many type 1 errors will you or how many tests you need to do to commit a type 1 error?
Are you
So,
asking how we know what the error is or just how often it happens?
how often?
So just going off the percentage, does that just mean 5 and 100 times?
Yes. Of course, now I'm jumping out. Let's see here. Right, but it's actually more than that. So, of course, now I've completely forgotten the logic. Just give me a moment. Let's go back to a chapter 6 here. So right, so okay, now I've got the logic. Right, so it's 5 out of 20. Sorry, 5 out of 100. It's 5 out of 100. But if we simplify that, so 5 divided by 100, so that's 0.05, that's 1 out of 20. So every 20 tests that you run, you get it wrong. And so the more times you run a statistical test, on your data in different ways, but every time you run a new test, you have a higher chance of committing a type 1 error. So the issue there is that you don't want to do multiple tests. So when you do multiple tests, you end up increasing your likelihood of a type 1 error. And so to get around this and to deal with this, the statisticians developed a way of testing all possible combinations at the same time. And what came out of that, back to the book. The reason why I'm using the book is that I've lost the lecture that I had for this. I don't know where it ended up. Hello. There we go. What came out of that, that issue of the type 1 error, is the analysis of variance. And what the analysis of variance sorry, the vet's calling. What came out of the analysis of variance, or what came out of this issue of multiple, the issues of multiple tests, came the ANOVA, which allows us to take multiple groups. So let's say species Setosa, versicolor, and virginica, and compare them to each other, and see if their group means are different in one single, what we call omnibus test. And that allows us to test these different combinations without having to deal with the issue of increased likelihood of type 1 error and thus a loss in degrees of freedom. Because also every time that you do another test, you actually lose another degree of freedom. So that's why we do it. We do this omnibus test because it gives us information that that allows us to decide, okay, is it now worth this risk of type 1 error to compare these different means to each other? And so maybe that makes sense, maybe it doesn't, but I think in practice, once we're practicing through it, it'll make a whole lot more sense. So what ANOVA does is allows us to compare the means of multiple groups to each other by analyzing, you guessed it, their variance and whether the variance between groups is the same or different than variance within groups. So let's take it step by step and build the ANOVA equation, and then we can learn how to run it. So first off, the ANOVA hypothesis is very, very similar to our t-test hypotheses. So a two-sample t-test is that mu1 equals mu2. A two-way ANOVA, meaning that there's a one-way ANOVA basically means that there is some measurement that we have, let's say sepal width, that we're interested in the average of, and we have one grouping variable that has more than two groups. In this case, we have three groups. And the hypothesis would be that the mu of group 1 equals the mu of group 2 equals the mu of group 3. If we had a fourth group, it'd be the mu of group 4, etc. We can have as many groups as we want. And then here's the important part. The alternative hypothesis is that at least one of the mu i's, so I represents the group, is different from the others. And so here we have no idea which ones are different. So ANOVA only gives us so much information. If our null hypothesis, if we do not find evidence to reject our null hypothesis, then we can confidently say all of our means are the same. But if we reject our null, we can say at least one of our means is different, but we can't say which one. We then need to do more tests to figure out, okay, which ones are different. And so that's why we call ANOVA an omnibus test. It doesn't really tell us anything except for there's some difference. We don't know what the difference is, but there is some difference. And we don't know how many differences there are. It's simply at least one is different. Maybe more than one is different, but at least one is different. And so ANOVA is just the first step in running in your statistical analysis if you reject your null hypothesis. Of course, if you reject your null, if you fail to reject your null, then you're done. There's no more analysis that needs to be done. So ANOVA, let's get through all this. The ANOVA is very simple. You calculate what's called an F ratio. So here the ANOVA is instead of being based on the t distribution, it's actually based on what's called an F statistic. And if you recall from the chapter on two-sample t-test, we use the F test to decide if the variances are equal or not, right? That's one of the assumptions of the two sample t-test. Well, ANOVA allows us to use that same sort of test, a test of whether variances are equal, but instead of looking at the variance of group 1 and group 2, we look at what are called the variance in the group mean square and the variance in the error mean square, and we take the ratio of that to figure out okay, are they or aren't they statistically significantly different from each other. And we can call the group mean square MS group, and we can call the mean square error MS error. And these we have to calculate. These are not just numbers. They're actually pretty detailed equations that we need to make sure that we understand well, because they can get out of hand really quickly if you get sort of bogged down in the mathematical nomenclature. And then, so that's the equation, it's the simplified version. And with ANOVAs, we always produce what are called ANOVA tables. ANOVA tables are relatively simple. It includes the sources of variation. So these are your X's. So in here, in a one-way ANOVA, we always have a row that's groups. So that's, in this case, it's treatment. If we're looking at iris data, it's species. So we know there's 3 species. And you have a row that's error. And that is and I'll explain what that is in a second. And then you have a total. And so you can add the groups and the errors together. The group sum of squares, so because we have to actually go from sum of squares to mean squares. The group is the group mean squares represents the variation or the variance, the difference in variation between different groups, so between all 3 species. The error mean squares represents the variance within each group. And so basically an ANOVA is asking, okay, is the differences between groups greater than the difference within groups? Because if the difference is, so the theory behind that is that if each group is more similar to themselves than they are to the other groups, then they must be different from different populations. If the differences among groups is the same as the differences within the groups, the variance within the groups, then they should all be from the same group, right? That sort of, does that make sense? Because if they're all from the same population, right? If all 3 groups are actually just subsets of the same population, they should be from a population with the same variance, right? Same mean, same variance. If each group has their own different, what we call variance structure, or they all have different variances within their groups, and they're different than what's between the groups, then we can say we're pretty confident that those groups are actually from different populations. And that is sort of the underlying theory behind ANOVA. And so we need to figure out, okay, what are the variances between the groups? What are the variances within groups? And we do that by calculating the sum of squares for the groups in the error, and then determining the mean squares for the groups in the error. And those equations are here. Look a bit messy. and here, the sum of squares. It's the sum of squares total. This looks a bit crazy, but it's not as bad as you might think. And so basically, we have what's called, so first off, to get the mean squares, we need to figure out the sum of squares. And we've already dealt with sum of squares in the t-tests. But here, now we need to figure out sum of squares groups and sum of squares error. And we need to figure out something called the grand mean. And that's the mean of all the data groups combined. And so I'm gonna show, all of this is in chapter 15. I'm not going to go through all of these equations individually because we have them in the R script, and I think it's going to be a whole lot easier if we look at it in terms of R instead of in terms of what's in the chapter. You should definitely go back and look at the chapter while you're working on your ANOVA your ANOVA portfolio page. Okay, so let's all open up R. And take a look at our, let's take a look at our ANOVA.R script. I provided you with the hypothesis. This is basically a copy of chapter 15. So we have the hypotheses here. And then I have here the very simple F equals MS group divided by MS error. This, of course, will not run because we haven't said what MS group is or what MS error is. So we can't really do much with that yet. And so to get the mean squares of the group, the mean squares of error, we first need to calculate the sum of squares group and the sum of squares error. And so we have to do what's called partitioning the sum of squares. So let's take a look at data iris really quick. So run data iris and then write head iris. And you'll get the first 6 observations of the iris data set. Now, when dealing with multiple groups, we need to make sure that we understand that we're looking at 2 different things. We're looking at individual observations, and we're looking at groups, at different groups. So when looking at a particular observation or particular Y, we can think of it as Y sub I J, where I equals the group and J equals a particular observation. So, for example, if we're looking at, let's look at sepal length. And we look at this observation 5.1. We know that, and this is from species Setosa. So we know that there are 3 species of iris in the data set. So this observation, this Y, is Y sub 1, which is Setosa. If we think Setosa is 1, Virginica is 2, and versicolor is 3. Then this Y is Y sub 1, 1. So J is 1 and I is 1. This one here, 4.9, would be observation 2, observation 1, a sub 1, 2. This one would be sub 1, 3, 1, 4, 1, 5, 1, 5, 1, oh, I'm highlighting this in the wrong, oh no, I am, I'm good. and this would be 1, 5, this would be 1, 6. And so we need to make sure that we know, okay, this is an observation 1 from group 1. This is observation 6 from group 3, or et cetera. We need to know those different things because it's important that we keep them separated, because we need to make sure that we know, okay, this data is associated with this group. These observations are associated with this group. This observations are associated with this group, and these observations are associated with these groups. And so whenever you see something like here, we have IJ. I is talking about the group, and J is talking about the individual observation. So what we need to make sure to do is figure out, okay, this is the sum of squares groups is the so what we need to do is we need to figure out, okay, what is our sum of squares of our groups? What are the sum of squares of our error? All right, realize there's a typo here. So these actually should say this. Oh no, they're right. Oh, right, 'cause it's y bar. Okay, so these are the equations for this whole sum of squares. But let's just skip down right to dealing with the ANOVA equation here, and we'll use these later. So just keep these in mind. Okay, so we have data iris, and what we need to do first is we're going to decide. Okay, well, let's compare all the sepal widths for all 3 iris species. And so first thing you want to do is figure out the means and variance for each of your groups. So in our case here, I have y, and we're going to call them yi, right? So y1 would be all of the sepal widths from iris species equals setosa. So if we run that, we also need our number of observations. We need our y bar 1 and our variance 1. And of course, we take a look. Here are all of our observations. N1 should be 50, y bar 1 is 3.428, and our variance is 0.14. Something we've done hundreds of times already, or at least multiple times. We want to do the same thing for versicolor. I guess versicolor starts with an E, so that's going to be number 2 then. And then our third one will be virginica. And so now if you look on your top right-hand side, we have N1, N2, N3. All of these are 50. They don't need to be equal, but it helps if they are. You see we have our variances for all three of our groups. We have vectors for all three of our groups, and we have our averages for all three of our groups. Put a thumbs up once you have all of that. And that's all the information we need to then just fill in our equations. So the next thing we need to do is get what's called a grand mean. And I call that y bar total. And basically the grand mean is just the sum of each n times the average for that particular group divided by the total number of observations, or we call that big N. So little n is number of samples, big N is the total number or little n is the total number of samples per group, and the big N is the total number of samples altogether. So here, big N is simply the sum of N1, N2, N3. If we run that, get that, it's 150, which should make sense, right? Because it's 50 plus 50 plus 50, or 50 times 3, 150. Now, the y bar total is a little bit more complex. So it's the sum of n sub I times y bar sub I. So I are the groups. So we have groups 1, 2, and 3. So it's n1 times y bar 1 plus n2 times y bar 2 plus n3 times y bar 3. And then we divide that by n, which is 150. So this gives us a total average, call it a grand mean, because it's all of the average. It's basically the average of averages. Run that. There we go, and it should be 3.0573 repeating. Now that we have this grand mean, we can actually now figure out the sum of squares. Sum of squares requires this grand mean to run. In the book, the grand mean is represented by y bar. And so the sum of squares is simply the sum of the n sub i's times y bar sub I. So that is the mean of group I minus the grand mean squared. And so if we take a look at our script, I have that here. And it's pretty big. So I'm going to pull that out a little bit. So it is, so we need to make sure there's 3 of these, right? So we have n1 times, and then in parentheses, y bar 1 minus y bar total, or our grand mean, squared. Then we add that to the exact same thing for n2. We add that to n3. And if we run that, it gives us SS groups of 11.34493. Is everyone able to replicate that? Now, SS error is a bit different. SS error is the equation sum of yij minus y bar I squared, but it can actually be simplified into the sum of the standard deviation. So see s squared of I times n sub I minus 1. So if we look at, you don't have to worry about how that could be, why that works that way. One of the nice things of this not being a math class. And so I'm sorry, did I say standard deviation? I meant variance. It's the variance. Sorry, it's that I read sample standard deviations, but ignore what I said. It's the variance s squared of sub I times n sub I minus 1. So take a look back at our script. So SS error is var1, which we've already calculated over here, times n1 minus 1 in parentheses. We add that to var2, n2 minus 1, then var3, n3 minus 1. We run that. And then we have SS error to 16.962. And we can add those together by SS error plus SS groups. We run that, and that's 28.30693, repeating. Are we up to that point now? Has everyone been able to recreate that? And I'm giving you these equations so you can copy and paste them into your portfolios. I'm not making you write these from scratch. Though it might help to do that so you understand the concept behind it, but it's okay. All right, so then we need to calculate the mean squares. And so we have MS groups and MS error. And so MS groups, really simple. It's SS groups divided by degrees of freedom of the groups. And so degrees of freedom is the number of, for the groups, is the number of groups that you have. So how many groups do we have with the iris data? If we're looking at the different species, how many groups do we have?
3.
3. So what would be our degrees of freedom?
2.
2. Yeah, it would be 2. So our group's degrees of freedom, k minus 1, or sorry, it would be n minus 1. I don't know why I put k there, but so n minus 1. So our number of groups is 3. Our MS groups is just simply our SS groups, which we already calculated, divided by 2, or divided by k minus 1. Run that. And so MS group should be 5.67, 2, 4, 6 repeating. MS error is just as easy, but in this case, the degrees of freedom are a little bit different. So it's the MS error is the SS error divided by the degrees of freedom of the error, which is the number of observations altogether, or big N, minus the number of groups. So how many groups do we have again?
3.
3. How many observations did we have altogether? What was
150.
all right, 150. So what is our degrees of freedom for our error?
$129.
Well, it's 150 minus 3.
Oh, 147.
So it should be 147. So we run that MS error, we should get 0.0.115387, whatever, all these numbers. Okay. Now that we have MS group, which is 5.67, and our MS error is 0.11, we now need to figure out, okay, what's the ratio of those two? How close to 1 is that ratio? The closer it is to 1, the closer they are to being the same number, right? Because if you divide the same number, right, let's say 2 and 2, you get 1, right? And so the F basically is telling us, okay, what is the ratio? And for here, our ratio is gargantuan. It is 49.16. That is nowhere near 1, is it? Everyone see that? So 49.16 is really, it's much bigger than 1. Could be much smaller than 1 as well. But the ratio is quite large. And so we can guess, okay, what it, I bet our p-value is going to be pretty small. We can actually use an f p-value, and actually the way to do it in R is using what's called the PF function. And here, the way to get the calculate the p-value, you do q equals f, and then you need to tell it what your 2 degrees of freedom are. So our degrees of freedom 1 is k minus 1, or it's the degrees of freedom for the groups. And then our degrees of freedom 2 is n minus k, or degrees of freedom for the error. And in this case, we only want a one-sided p-value. I'm sure I say in the video why that is. I cannot remember why that is, but that's what we do. So that's how you would, so those steps is how you would do an ANOVA by hand in R, which is clunky, annoying, and you'll only have to do it once in your portfolios. Now, the thing about ANOVA is that we just produced a ton of information. We produced, what did we produce? We produced degrees of freedom. We produced sum of squares. We produced mean squares. And we also produced an F value and a P value. And so when you're reporting these sort of results from an ANOVA, you want to use what's called an ANOVA table. Let's see where it is. So this is an example of an ANOVA table. And these are all numbers that these aren't the numbers we came up with, but these are all examples of numbers like the ones we came up with. So in this table, and I already showed you this, but now we have the numbers to fill it. We would have the group, a row for the groups, and a row for the errors, and then a row for the total. We would give the sum of squares that we calculated, both group sum of squares, error sum of squares, and total sum of squares. We would provide the degrees of freedom and the total degrees of freedom, which should equal the number of, it should equal the number of observations minus 1. Yes, it should, I believe, yeah. And you also provide the mean squares. You don't take the total mean squares. You provide the 2 mean squares, and then you figure out the F ratio, and then you provide the p-value. So for us, all of that information lives over here. And so our sum of squares groups, 11.34. Our sum of squares error, 16.96. Our sum of squares total is 28.31. If we round up. Our degrees of freedom, our first degree of freedom is 2, so it'd be, so let's see, so k minus 1, which is 2, and then n minus k be 147, and then 2 plus 147 is 149, which is,
Dr. Lundquist,
yes.
we
Oh,
still,
I didn't flip that. Sorry, didn't flip that. Sorry. So we have it up here. So we have our sum of squares groups, which is 11.34. Sum of squares error, which is 16.96. Our sum of square total, which is 28.31. We have our degrees of freedom. Our first degree of freedom is k minus 1, which is 2. Our second degree of freedom, our degrees of freedom for our error is n minus k, which is 147. And our total degrees of freedom is 2 plus 147, which is 149, which is 150 minus 1. So it all comes together. We have our mean of squares groups, which is 5.67. Our mean squares error is 0.11. And we have our F ratio of 49.16. And we have our p-value of itty bitty teeny weeny. So it's like negative, we basically would call this p is less than 0.001. It's really, really small. But guess what? We can produce an ANOVA table in a matter of seconds by using, it's called the AOV function. So AOV is ANOVA. There's different ANOVA functions in R, and I'm not going to go into the differences in them because I still don't really understand them myself, but the AOV function works for what we need. And so the AOV function, let's type this together. So it's AOV, and what it requires is a formula. And so if we're interested in the differences in the sepal widths, we write sepal width. So that's the name of the vector that we're interested in, the name of the name of our y, right? So these are the observations we're interested in. We then use the tilde function, which is shift tilde, which is on the top. See if I can show you on my keyboard. All right, so if you take a look at the keyboard, focus. Okay. So we have shift, and then right above my tab, there is this button here that has an accent and a tilde. So press shift and that tilde button, and you'll get that little squiggly line. Everyone able to find that key? I believe it's in the same location on a Mac. So shift, and then this key right here. Shift, and then this key right here. And that is a part of the formula. And I always think of that tilde to mean given. So sepal width given species. And species is our grouping variable. So we have our numerical continuous variable, sepal.width. And we have our grouping variable, or species. If you notice, I didn't write iris $sign sepal width or iris $sign species. It's actually much easier and cleaner to tell it what the data is. So we actually tell R, okay, data equals iris. And so basically what R will do, it will look in the data set, the iris data set, for a column called sepal width and a column called species, and then run all of these ANOVA equations that we did and pop out a ANOVA table for us. So if we take what you wrote and you run it, it will pop up this here, which is our ANOVA table. Or at least some of the numbers. They haven't really, actually hasn't given us everything. What it gives us are the sum of squares, so our group sum of squares, and it gives us our residual sum of squares, right? And those numbers match, right, the ones that we calculated. Everyone see that? It also provides us with our degrees of freedom. There's 2 and 147, which makes sense. But it doesn't give us the full ANOVA table for some reason. It does give us the residual standard error. Residual is also another term for error. So the, let's see here. We don't have to worry about residual standard error quite yet. But if you notice, there's a species residual. So group and residuals just means error. So in R, when they talk about residuals, and we'll talk about residuals more when we go into correlation and regression, but residuals is just is synonymous with error. And so to actually get the R to produce a ANOVA table, we actually have to use that summary function that we used way back in I think chapter 2 or chapter 3. And so what we need to do is we need to call our ANOVA equation something. And so here I usually call it a model because we're using an equation. So here I just called it model.1. So I run that, and now has these species and error sum of squares, or group and error sum of squares hanging out here. Then if I run the summary of model.1, that gives me a proper ANOVA table. So here we have species and residuals. You can also think of it as group and error. Degrees of freedom, 2 and 147. Okay, that's correct. That's same as what we calculated. Our sum of squares for our group is 11.35. That's correct. Sum of squares for our error is 16.96. That's there. It doesn't give us the total, but we can always calculate that if we want. Mean squares, 5.672. That's right. And then 0.115, the mean squares of the error. That's also right. It gives us our F value, 49.16. That's right. And then gives us a P value that's extremely small. That's also correct. When R provides you less than 2 times 10 to the negative 16, it just means it's really, really small. And so you would report that as P is less than 0.001 or something like that, just to indicate that it's really small. And that's pretty much it for an ANOVA. So what is the interpretation of this p-value? What is our interpretation?
It's really, really, really small.
So what's the statistical interpretation based on our null and alternative hypothesis?
We reject the null.
So yeah, we reject the null, and therefore, what can we say about our differences here?
That there are differences in the variances.
How many? There's differences in the means. That's what we're actually, it's a call analysis of variance, but the hypothesis is about the difference in the means. So our null is that the means of all 3 groups are the same. So what's our alternative?
Just that all 3 means are different,
That all of them are different?
or at least 2 of them.
At least 2?
Okay, I'm just wrong on all that. 1.
No. So, well, that's the thing, right? It could be. No, you're not wrong. It's just that we don't know. So it could be 3 of them are different. All 3 of them are different. It could be that 2 of them are different than the other, or only 1 of them is different. And so you're absolutely right. All of those are possibilities, but the test doesn't tell us that. It can't tell us. What it tells us is okay, at least 1 of these is different, but maybe all of them are different. We don't know. And so that's why we have to be careful about what the test actually says versus what the actual reality might be. And so, and this is important because now we know that these are different. We know that our p-value is really small. Now we can actually go ahead and do some more tests to do what are called post hoc tests, or tests after the fact. And I'll skip the R² for now. And so what we can do is we can do what's called a 2-key test. And a 2-key test, you don't have to do this by hand, because it's really annoying by hand. It's called 2-key Kramer honestly significant differences. So 2-key HSD, and all we need to do is run that function with our ANOVA model in it. If we run that, let's run the whole thing. If we run that, we get this. And you can ignore all of this, this diff, lower and upper. But if you see here, we have 3 different combinations. We have versicolor setosa, virginica setosa, and virginica versicolor. Everyone see that? And at the very end, we have something called P adjusted. Anyone have any reason why, any idea? It's on here actually, but remember in the beginning of the session today, I talked about type 1 error. And the more times that you do it, you analyze the same data, the likelihood of you committing a type 1 error increases. Well, there have been a number of folks, particularly this gentleman named Bonferroni, who developed a way of adjusting p-values based on the number of combinations that you do to make your data more conservative, make your analysis more conservative, therefore make it less likely for you to commit a type 1 error. And basically a Bonferroni adjustment is taking your p-value and dividing it by the total number of combinations. So here it'd be your p-value divided by 3. But you don't need to worry about that. You just need to know that the p-values are adjusted for multiple comparisons, for the fact that we did 3 different comparisons. But if you look, our p-value, our adjusted p-values came out as 0, 0, and 0.008 or 0.009. These aren't actually 0. They're just so small that there weren't enough decimal points to show what the actual number was. And this one is also really small. So what does that mean? What is our interpretation based on this post hoc test? Which means are different? Anna?
Sorry, I stepped away for like half of that, so I only caught the last half.
So look at these p-values, which are adjusted for multiple comparisons. What would you say?
So is versicolor, is that where our difference is?
Well, how many of these p-values are significant?
Well, only versicolor.
Look how small they are. So these are sorry, you guys stepped away from, these aren't actually 0. These are like, they're just so small, there weren't enough decimal points to show them.
Oh.
So how many of these are different?
So none, well, all 3 of them?
All 3 of them. So you were right.
Okay.
So you're saying that all of them were different. You actually, in fact, were right. So because these p-values are 0, so our hypothesis here is that the means are the same. And our null hypothesis, and our alternative hypothesis that the means are different. Run Tukey HSD. We know at least one's different from the ANOVA. And then running this test, we're like, oh, all 3 of them are different, which is super interesting. And then we can start to make some claims about what the world looks like in terms of these versicolor sepal lengths or sepal widths. So that ends the session. I will put this on a recording or have been recording, so I'll put it up on Brightspace and YouTube unedited. But one thing I want you all to make sure you know. If you run a ANOVA and this p-value is greater than 0.05, you cannot then run a post hoc test. Due to the fact that type 1 error is possible, and it's still possible for you to run these Tukey this Tukey test after a non-significant p-value in your ANOVA, it is possible you could get significant differences, but they're not valid because your ANOVA did not detect a difference between the groups. So let me reiterate. If your ANOVA is significant, p-value is less than 0.05, then you can do a post hoc test. You can do a 2-key HSD. If your ANOVA is not significant, you cannot then do a post hoc test. You end at the ANOVA. The ANOVA is done. The ANOVA is your last step. Okay, so that's all I've got for today. Thank you all for joining me. I'm a little disappointed that we had such a small turnout, but I'm glad that you all had the time to come and go over the ANOVA stuff. Definitely watch the video. I basically just went over the same thing I went over in the video here today. Make sure to watch that. It's a bit longer, but it's definitely worth it because the ANOVA is probably one of the most powerful and most useful statistical tests that you'll learn in this class. So to make sure that you got it down, because I use it all the time, and you'll find that you'll use it quite a lot if you go into grad school or you go into med school.
Thank you so much.
Have a good one.
Have a good
You
day,
too.
Professor.
Let's stop share.